Hey everyone, welcome back to the Summer Pi series, and in this video we're finally gonna build the convolutional neural network that we've been talking about in the past couple videos. So to start off, let's create our neural network class, which I'll just name convolutional neural network. And we're going to inherit the torch.nn module, the neural network module. So a lot of the stuff that we do here will be very similar to the process that we use when we built our fully connected neural network. So then we'll need the init method as well. And to initialize our network, we're going to need to pass in the number of channels that we're using. So our images are colored, so there's 3 channels. And then we also want to pass in the number of feature maps. Remember, convolutional neural networks build these feature maps that encode the patterns that it sees in the images. We'll also need the super function again. So convolutional neural network. And then we could start to build our CNN, and we'll use the sequential method as well. But before we start adding any layers to this network, let's start to keep track of the data as it goes through the network. So our inputs are the images. So we have a number of channels, which will be 3, but we just named it NC so that you could have the freedom to change this for other types of images. And our image sizes are 64 by 64. So now we're gonna add our first convolutional layer. We start with the number of channels that are coming in, and then we put the number of channels or the number of layers that we want out, so the number of feature maps. We'll have a kernel size of 4. Remember, that instructs how to traverse through the image and scan for the patterns. We'll have strides of 2 and a padding of 1. Now, once you apply this convolutional layer, you're going to end up with a number of feature maps of size 32 by 32. In a previous video, we talked about how the size of your inputs coming in, the size of your kernels, your stride, your padding, all plays a role in the resulting size of your feature maps. So if you haven't practiced that yet, I do have a code on the GitHub that will help you test whether or not you're able to evaluate what the correct size of our feature maps will be. So if you want to try that, check out the CNN_test file in the ProjectYumo GitHub. And then continuing with our neural network, we're going to want to apply the batch normalization, and we're normalizing the number of feature maps. We're normalizing all those layers. And then in a previous video, we also talked about why it's good to use ReLU, so we're going to use it here as our activation function. So we finished our first convolutional block basically. We apply the convolution, we normalize the layers, and then we apply our activation function. So we're going to repeat this process again. But what happens now is in your next convolutional layer, you're accepting in the number of feature maps you just created. And what we're going to do is we're going to multiply the output by 2. The reason we're increasing the number of feature maps we have is because as you go deeper throughout the network, we're creating more abstract features, and it opens up a lot more possibilities for the types of patterns that we could recognize. So to be able to capture all of it, we're going to want to increase the number of feature maps. We're going to keep the same kernel size, the same strides, and the same padding. But what happens now is your feature map dimensions get cut in half again. And then the number of layers we have is multiplied by 2. We're going to need to change the number of layers we're normalizing, so multiply that by 2 as well. And then let's repeat this process again. We're going to repeat this process until we come up with a prediction. And there's multiple ways to use a convolutional neural network. You could add fully connected layers at the end, but we're going with a fully convolutional network, and you'll see why this happens. So the number of layers coming in is NFM times 2 now. We're going to increase the number of feature maps, so times 4. Keep the same settings for our kernels, And now our dimensions are going to cut in half again. Increase the number of layers. Repeat this process again. This time it's ×4, and we're going to create ×8. Now our feature maps are 4x4, and we have NFM ×8 of them. Now we can apply our final kernels to the 4x4 feature map, and we will be left with a prediction. Now let's apply our final convolutional layer, where we have a kernel 4 still, but a stride of 1 and a padding of 0. This way we're only left with a 1x1 block. And we're taking in the number of layers ×8, and we just want a prediction, so we'll change this to 1. So now what we're left with is a 1x1x1 result, which is our prediction. It's a single number that defines the prediction that the neural network made on the image sample. So since it's a prediction, we do want to scale it between 0 and 1, and the best activation function to do that is the sigmoid function. And that's it. We've built our convolutional neural network. All there really was to it is to get the dimensions down until we could come up with a prediction. This is a fully convolutional neural network because we only use convolutional layers to extract the patterns. Sometimes people like to add fully connected layers at the end, and we'll do a comparison on that in a future video. So now all that's left to do is to create our forward method. So define forward, all we need to do is take in our inputs and then return the predictions that the CNN makes when we pass in our inputs. So we should add an S here because input might already be defined in Python or in one of the libraries we're using. So now we've built our convolutional neural network. We're going to learn how to pass in the data we processed previously and train the model, and we're going to get a sense of how it performs on image data. So we'll do that in the next video, and I hope to see you there. Peace.